of the graph neural networks, or the GNNs. So we said the graph neural networks are specialized class of neural networks designed to handle and learn from graph data. So it has the spatial features. Now, I was listening to a video over the week, and somebody was talking about the evolution of humans and the current state of AI. And the specialist was scared that with the way AI is going, there would be a point in time where humans and AI will have to merge, which is what we call transhumanism. Now, when that point comes, he is scared that humans will begin to lose some abilities that makes them human, such as the cognitive thinking and empathy and such of emotions, losing it to the machine. Now, he begins to make comparisons of how the early humans evolved from the Homo habilis, Homo erectus, and all that to the current Homo sapien we have. And he was like, the next evolution is likely going to make the current human abilities to win out. Now, the same way you see that the traditional neural networks cannot be able to handle this complexity that comes from the the graph data. So because of that, we can't be able to use them, but they can be able to give us information that could help us to be able to design a network that is specially packaged with the abilities to handle the graph data set. So we said the graph neural networks has special functions that helps it to be able to learn from representations we call embedding. And this embedding is simply taking these nodes and edges, putting them in what we call the embedding space, or the entity, or the entire graph. We can be able to study it by looking at the nodes, which we consider them as features, and also the edges or the relationship, which we say the graph structures entirely. Now, the geometric deep learning, GNNs, are a form of geometric deep learning. So it has also that sort of coordinates, because of course we are talking at nodes and edges. So it's sort of a geometry, because if you know the graph is a sort of a geometry. So the GNNs is powered by these abilities to be able to establish this sort of coordinates, to be able to study this relationship between these nodes and edges. So the GNN is what enables things like social networks, molecules, and knowledge graph to become a reality. So if we have the graph, a simple representation of a GNN, if we have the graph, we can be able to feed these inputs and then use this sort of multi-layer perceptrons to carry out all the activation function. Remember, we talk about those things in the normal graphical neural networks and all those transformations, and then be able to successfully output a graph that has that established relationship, either at graph level, node level, or edge level predictions. Okay. Now, the key concepts that you need to understand in the graphical neural networks is, one, the message passing. Now, the message passing is a mathematical function that is used to aggregate the node information around its neighborhood. Now, if we have the target node, we are able to look at all the information around it and be able to come to a conclusion. Because when we learn this information, we can be able to know if the relationship is strong, weak, or even if it doesn't even exist in the first place. So the node embedding learn the future vectors per node, and the graph level outputs will output the whole graph either as a classification problem or a regression problem. So what the message passing does is that when it looks at each of the node, it will begin to do some sum up. It will also do some adjacent matrix sort of insight. And then at the end of the day, it will output this weight that will tell how strong that relationship is, with each of these nodes. Now, somebody may be asking and say, but how about if we carry out some sort of permutations? Would that change this weight or the arrangement of the neighborhoods around that node? It won't be able to change. It won't alter it. It won't cause any harm when we altered the arrangement of the nodes. It's kind of constant. However, that would help. We have to come up with a concept of invariance. Sort of, and like I always say, I don't like bothering you with the heavy mathematical side of this, but the concept of the invariance is to help us to be able to understand or to carry out these sort of computations around that particular node, and then to be able to still determine if it's going to be important or not. Now, the paradigm of this message passing, we said the core concepts that the graph neural network operates is via that message passing. The process involves first, it generates a message where each node creates a message based on its own future and those of its neighbors. Then the next thing it will do is to aggregate that information it creates. Like I said, it will create a sort of matrix like we have talked about, that adjacent matrix. So it will create that and then it will do the calculations there. Then it uses this concept of back propagation, like we saw in the normal recurrent neural networks. It will do that to update the loss function to see if it has learned something or it doesn't learn anything. So when it does that first aggregation, it does it sum up all the information around that neighborhood of the node. It passes it again to the next layer. Let's say it does the aggregation and all that. The next time it will update the node information. So the node updates its own state or representation using the aggregated information and its previous state. So this back and forth via back propagation will help it to begin to see if it's learning the right thing or not. So the goal is to iteratively capture local or global structure of the graph. So if this is the input of the graph, it will first of all use that message generation to be able to capture the relevant information around that node and all its neighborhood. Then it aggregates, it updates, and via back propagation, it go back again to see what happened if the loss function is much or small, back and forth. And the message in this case that we are talking about is not, it's just looking at the source of the node, the edge, and the target node, stuff like that. So it's not like it's a complex thing that it's looking at. It's just that relationship that exists and how close this node is to its neighbors. Now, having understand that, you also need to understand that just like in the traditional deep neural networks, we also have these different architectures of the GNN. One of it is the graph convolutional neural network, that's GCNs. when we say GCN, it's not these ones that they talk about in Nigeria. We're talking of graph convolutional neural network in this case. Now, this is an extension of the convolutional neural network concept, but in the case of graphs, where we aggregate the neighborhood information around that node and then uses the convolutional operation of max pooling, remember, and all that, and decoding and all that we saw in the convolutional neural network to carry out the operations. Then there is the graph attention networks. We call it GATS. Now, the GATS approach or graph attention network introduces this attention mechanism to assign different weights to message from neighbors, focusing on more relevant information. Now, remember I told you guys when we were in the previous class that things like large language models sprang up after this paper that was published on the title was Attention is All We Need or something. Now, when you looked at that particular paper, you will see that the recommendation from the authors was that they need to design this architecture that will pay more attention to a particular token also, and based on that paper, when you begin to look at that and looking at the real facts from the early statisticians that like Turing, that talks about this giving this weight to words in English, you will see why the ChatGPT and all those large language models performs very well like a normal human being, because they came to realize every words are not the same. Some of it should carry more weight than the other and all that. So the same way, this sort of graph attention networks, they are part of some of the things that culminated to the current large language models you see we have in existence. So that attention mechanism help it to be able to focus more on the nodes that have more weight or information and leaving out the ones that are not too relevant. We also have the graph autoencoders or GAEs. Now, this is used for unsupervised learning approaches such as graph reconstruction and dimensionality reduction techniques. So whenever you have unsupervised learning problems that you perceived they are graphical, they are represented in a graphical format, and you can be able to use this network, this is where it comes in to really help solve the problem for you. We have the recurrent graph neural networks, which utilizes the recurrent principles for learning sequential or dynamic graph problem. Now, there are times that you have problems that has to revolve around spatial, temporal issues, incorporating the time or location into it. So that kind of problem, that the autoencoder can't solve it, the attention can't, the convolutional can't. You just have to borrow from the recurrent neural networks. Now, let's look at each of these architecture in a bit detail by zooming into each of them. You will see that the graph convolutional neural networks, GCNs, we say it extends the CNN graph topology. It aggregates the neighbor in futures or information and refine it across the layers. So once we feed it the graph, such like this, it will, perform this sort of zooming into each of, at each layer. Remember the way the convolutional neural network works. it kind of partitions them into several pixels, grids, and then at the end of the day, zoom into it and perform some aggregation and all that. So it's similar kind of approach where once we feed the graph into the neural networks, it perform all those manipulations we see in the convolutional neural networks. And you can even use things like regularization approaches, maybe L2 regularization or L1 regularization, depending on what you're using, to drop out some of the nodes that are not important and focus on what are important. Then, of course, you have a layer for the max pooling and all that. And then you have finally the output layer where you could easily just output everything. So it could help. In this case, your prediction problem could be node levels. It could even be new links, or it could even be you are trying to recreate the entire graph. Now, remember we said it could be a graph prediction problem, it could be a node prediction problem, or it could be an edge prediction problem. So depend on what problem you are trying to look out for. So they said it's ideal for semi-supervised node classification task problems. And it has this spectral versus spatial ones that helps to incorporate things that has to do with location data and all that as well. Then when we talk about the graph attention network GAT, we said it introduces the attention weight on the edges. And then in learn which neighbor contributes the most. And then it improves the performance in the variable graph structure. So using that concept of attention, like we said, by the time it carried out all the aggregation around the neighborhood, it will quickly know which of them is important. And then during the encoding phase, it will be able to pay more attention to that, and then by the time you have the activation function works on it by transforming it, you'll be able to have this weight coefficient for the attention and give precision on what is important or not. Now, we also have the graph recurrence networks. Now, like I said, the recurrent network combine the principle of recurrent neural networks with the graph structure. So when we have a time variable alongside with the input graph signals itself, we will need to make it in such a way that the memory cell will be able to work on these three D sort of data, having the time variable inside. So remember the recurrent neural networks where it has the ReLU acting on it and all that, the encoder, decoder that we talked about in our last class. So it's still the same way where in the encoding form, we will perform some sort of graph convolutional recurrent layer. We do all the transformation there from one layer to the other. Then by the time we finish, we will also rely on the decoding phase to be able to, open up this layer for us in order for us to make a prediction. Now we said this design is done in such a way that it could be able to handle that temporal dynamics in the graph data, making them suitable for scenarios where the relationship evolved through time. Now, like I told you last time that in healthcare, if we are looking at a patient level data, sort of medications, and looking at some outcome that has to evolve in the process of time, if we are looking at treatment options, this is a very good place where we could put in this kind of network into. So the network will be able to analyze similar patients that undergo that kind of treatment. And it could be able to tell us if that patient is going to, for example, be treated over the period of 5 years, 10 years, 20 years, and so on. So this kind of graph recurrent neural networks, it's makes a lot of sense, especially when we are looking at windows of time, to be able to know how these graph relationships will evolve in time. Now, the spatial and spectral-based graph neural networks, it said that in the case of the spatial, it operates directly on the graph structure, focusing on the spatial relationship between the nodes. Then the spectral base, on the other hand, will focus on the spectral graph theory. It will utilize, the spectral graph theory and apply these techniques from Fourier transformation. If you remember, in maths, we have this Fourier transformation that help us to determine the spectral length or something. And then it analyzed them to define the convolution on the graph. Now, this is a very good example I picked up online. I couldn't really find materials as such on this, but this diagram actually helped to explain the spatial and spectral GNN for us very well. So if we have this graph data where it does the aggregation rationale, focusing on the spatial domain. And of course, when we talk about spatial, like I said, spatial data has to do with like maps, and all that. Could have this spatial ability and so many things. So by the time it does that, it could borrow things like polynomial aggregation approach, and then looks at all the connectivities, and then uses this linear transformation sort of approach to aggregate, and then passed it on to the spatial phase, as the spectral phase. Now, in the spectral phase, it will look at the edging values and do some sort of linear approximation, then also some polynomial transformation, and then it passes it on, using this rational approximation. So it's kind of complex approach. I'm not really too familiar with this spatial spectral, to be honest, but I think it's combined the both patterns to be able to make predictions